Okay. Well, that's me. All right, before we begin, all the technologies that I'm going to go over are valid. So those of you who have some religion on one technology or another, realize that I have to be pretty agnostic about it and just use what's out there. Everybody's got a different recipe. Most of them work. This presentation was meant to be conversational too for the TE panel. So let's see. Back in 1997, 8 or so, we had a nice frame network. Ran great. Had a GUI. GUIs don't work really well at our scale. You end up with a thick mesh of stuff that you just don't want to have to look at, you know? You got a CLI, works a little better. We didn't really need all that extra gear in the core either. But things are different today. Frames still out there, still in use. Let's see. Still using it. It's got some interesting mechanisms. We could still use it to share pos links. A lot of people don't do that. A lot of people switch to PPP. It's inexpensive StatMux gain. We use it to trunk up a lot of customers over frame switches. The switches tend to be a little cheaper than the routers. There's some interesting potential for policy routing that we actually haven't explored all of yet, and you might be able to do some interesting things with MPLS over frame as well. Link state prioritization issues, oh, they abound. There's a lot of problems, or there were a lot of problems with the frame network with link state prioritization issues. What happened was you didn't get sufficient priority on link state, so when someone would go through and start computing their SPFs, they'd drop links if they became too busy, or if there was congestion and a link dropped, then another link dropped, and then suddenly you had your whole core in flux. It wasn't pretty. I went through about 4 days of it back in 1997 or 8. We switched to ATM. With ATM, we suddenly became self-limiting at OC12. We, for a long time, didn't have a higher capability interface. ECMP helped a little bit. We overcame some of those limitations by massive parallelism. About 8 parallel paths you could take through the network. In some cases, that's still out there, actually. So is there a way we can do things a little better without having to go from one type of device to another type of device to determine the fate of the traffic? I'm going to suggest that there will be later. Once again, things are different. Some people have high-speed OC48 SAR. I don't, but that's one interesting mechanism you could use. One of the fun things that we had with ATM for a while was a UBR-VBR dual profile network, where we would have traffic at one time a day that was mainly UBR. It'd get queued differently, and we had another profile of traffic that was VBR. That was obviously queued in a more preferential way. It worked, but it became a headache again. It's a lot of complexity. I think, as Randy was mentioning, the complexity can kill. Frame to ATM mapping, that helped add some life to our edge switches, managed to get things scaled up a bit more. Of course, then you run into sub-interface issues. How many sub-interfaces can you manage and collect stats on? Once again, link state prioritization. In ATM, we had issues again, and the same thing with frame, where if you provision one IGP on top of another IGP, this is the overlay model that UNet's been very fond of for so many years. The thing about the overlay model is that if you run one IGP over the other and you run the one underneath congested, and let's take ATM, and you drop one cell out of every 5 or 10 for congestion issues, you're going to suddenly have flapping. We also had problems with the ATM switches with link state priority, where you would get a flood of traffic you would take a link offline, and that would cause churn. The churn would get worse, more links would drop, and it'd just get worse and worse. This is what we're doing today. That's today, not necessarily tomorrow. As you can see, we have a full mesh, planar full mesh of adjacencies across the transit core and a metro. Basically, those are fiber rings, but we provision LSPs to the rings. We use, oh, by the way, there's ECMP, of course, involved on the TLs, and so we get some load sharing there. So actually, this could be parallel paths. You could have, 4 or 5 or 6 of the links between the devices on using MPLS. It's latest and greatest. It's the big thing that everybody likes to do now, and it's got some good reasons. Simplified troubleshooting. It's much easier to troubleshoot when you're on one device and it contains all the information you need to troubleshoot your problem than to have to log into 2 different things. We can manage the flows directly on the routers. This has the direct benefit of allowing the IGP to be queued differently. Since we're fond of ISIS, ISIS gets to be in its nice separate queue from all the MPLS LSPs and all the IP forwarded traffic, and traffic still is IP forwarded as well in certain situations. So that got rid of the problems that you'd get with ATM somewhere in the middle of your network dropping packets and having trouble determining where that's happening. It's got some interesting failure protection that didn't exist in a lot of the other platforms where you get fast reroute, and it's a means to an end. It's just another way to get the host to talk. So that's all MPLS really means to me, at least. It's good, and this is like this with frame and ATM. It's good to pre-test your LSPs before recarving. You don't want to drop your LSP. I use RSVP to carry the traffic, and the RSVP LSPs are inserted into the IGP, which means that if I don't pre-test the LSPs, I end up with a situation where I can drop people's traffic. So I like to pre-test first and then build. On a large scale, flows are stable. We don't change the reservations on the flows very often at all. We change them about once a week, and only if they've varied by a certain percentage. It's a real easy way, using MPLS and IP combined, to determine what the latency is and actually engineer your network according to the latency and according to the needs of your customers to get their traffic through quickly. This is a nice way to do it, so that was a good thing. Very, very easy to manage. It takes not very much time at all. Link state prioritization is built in because it's all on the same device. You don't have to worry about a flood of traffic causing your IGP to go offline. Link-specific preemption, that's a pet project of mine that I've been hitting up the vendors for a while. Link-specific preemption means taking a specific link LSP combination and providing priority over that specific link and LSP. That does not mean that it is not the same as having the LSP priority. This is a mechanism specifically that would have addressed a problem that we had, or actually a very nice set of circuits that we had that went through Canada with a very nice latency that we couldn't take as much advantage of as we wanted to because we didn't want to starve out the resources for Canada. So we had to make those links less desirable in terms of latency, which was unfortunate. This is the which do you prefer slide. 8 parallel uplinks, 2 parallel uplinks, or 1? Well, 8's a lot. ATM kind of drove us to that. Redundancy's excessive, it's costly, it's complex. You want a certain amount of it because you don't want those calls at 3 a.m. but you don't want enough that it makes it harder for you to fix the problem or harder for you to find out where the problem is. ECMP is not very effective for tunneled and chunky traffic. That's a problem we've been experiencing. One link is not the answer simply because I don't want to be in a situation where I have to tell the customer I didn't provision redundancy. 2 for me is just right. If it's IP forwarding. MPLS tends to get kind of chunky though, it's not splitting right now. Tunneled flows at large sizes, they don't work very well over ECMP. Single source, single destination, single port, you just can't ECMP it. Fate sharing becomes the question. I've never had a satisfactory answer as to how much redundancy do you want. And if I can ever get one, it'll be fantastic. IGP, it's good for a general indication of where you want the traffic to go. It's something that I want to keep very stable because it's how I make decisions on what I send to my peers as well as my customers, and I want them to have a stable decision set. I don't want to change the IGP and change my selection of which peer to use based on a trunk going down somewhere. So I try and keep that flat, just the way UNIT's been doing it forever, and we let all the action happen on the TE and RSVP MPLS level. Some folks use it for a lot more though, so more power to them. It's a bit slow on the older devices, and I've got quite a few of those, so I try to make it so that they don't have to see too much of the action, and the action that they do see happens in a way that doesn't have to make them have to change their minds. MPLS and insertion of shortcuts into your IGP, that's pretty much what we do. So ECMP increased the lifespan of ATM dramatically. It really helps to keep ATM in the network for a lot longer. It's letting me reuse lots of interfaces. Has some implementation problems. There's a solution, a potential solution for ECMP if you're creating lots of tunnels, and some people will probably kill me for saying this, but potentially using a range of source addresses towards a single destination. A tunnel doesn't need to have the same source address, it just needs to have the same destination address in order to be established. We got a lot of routers and router vendors out there who base everything on a very limited set of information in the IP header. If you can use a range of source addresses, you can at least help to optimize ECMP a little bit. You could create multiple tunnels. I've recommended that before. IPsec, that bullet didn't really fit, but IPsec makes looking deeper into packets a little bit difficult. It randomizes a lot of the information that you would have used. IPv6 flow labels can help when we get IPv6. And of course, use it. It's a great thing to use, and it's better to have 50% of your customer upset than 100% of your customer. Watch out for the hash functions. I've been bit twice now by 2 different sets of people for somehow having a hash function that didn't quite work all the time. One of the things that I'd love to see is a key to the hash that I could just randomize on my own every once in a while. I still want it deterministic, but it'd be nice to be able to mix it up. BGP, and this speaks to Randy's comments quite a bit, it's not a good tool for traffic management. Yet there's, can be no other way at sometimes. Meds are broken. If you looked at Randy's presentation, he showed you one instance of using communities in ASPaths. Meds are another way to really screw up BGP, and I think VJ gave a presentation on this a while back. Oscillation is a pain in the butt. I have a hierarchical BGP. I run confederations, and on the border of the confederations, that's exactly where I'm going to have issues. Now, I've had to slow things down in order to make that go away. Hierarchy's good. So that's IP hierarchy, and having a mechanism to reduce the amount of information that all your edge devices have to carry is great. You can take it too far and induce suboptimal routing. so you don't want to go too far. But some hierarchy is good, and you don't need to know everything on your edge devices. Okay, conclusion. IP hierarchy is good. Parallelism is great. If you're perfect. MPLS and the other native backbone L2 mechanisms are boom. They're really helpful. And I think that, you know, I sort of pushed back on MPLS going native edge to edge for a long time. And I pushed to have the overlay model continue to be implemented in the AS701 backbone. We ended up with a happy medium, I think, and it's turned out to work really well to have the MPLS LSPs inserted in the IGP. Gives you the benefits of the overlay with the assurance of your IGP. So, thank you. Any questions? Sure. Maybe not. Okay.
Sue here's next top, also your moderator. Couple questions based on that. Comment on IGP is slow on some of your devices.
Yes.
Can you be more specific? And then what happens when you eventually get the software loads to go fast?
Well, it's more a matter of size. We have something like 1,000 nodes in a network that have to converge, and we want to get them to converge really quick. I've got some rather antique edge devices, which, because we've all gotten really cheap now, I don't want to have to upgrade. In fact, I'm not allowed to upgrade. So I have to have mechanisms to keep those things running. The SPF just takes, sometimes I don't even get code for them, you know, or they're very hard to get code for. You know, the SPF takes a long time, and it's just going to continue to take a long time. So reducing information and you know, removing the amount of CPU usage helps a lot.
Second, another thing you mentioned is you slowed down on your confederations at the edge.
Oh, I had to basically between the confederate and the sub-AS boundaries. You could watch actually when people started using meds, and it takes 3 parties to make the med problem really nasty. With certain people using their meds, they would cause an oscillation. The oscillation goes really fast. Get your CPU running about 50% on devices that are pretty powerful. The way that we had to fix that with one vendor at least was to slow down the propagation of BGP information. So, which is unfortunate. I'd like it to go, you know, lightning speed across the network. So,
Thank you very much.
yeah, thank you. Any other questions? I see someone getting up. Maybe he's going to the bathroom. No, he's coming to ask me a question.
Brian Dixon with Argonet.
Hey.
Question about scalability. We're talking about the convergence of your IGP.
Mm-hmm.
Does using have you looked at using hierarchical deployment of either within an IGP or using possibly multiple IGPs to do, you know, scalability?
You know, that's
obviously one thing that leads to that is that can only work if your allocation policies for your networks.
That helps a lot. Absolutely. And if anybody who remembers UNet knows we did a horrible job of allocating internally to start, and we've gotten a lot better now. Those who might remember, we've actually done a lot to renumber things. We've had a lot of conversations about hierarchical IGPs, and I, by the way, just to preface this the way everybody does, I'm not speaking for MCI, I'm speaking for myself. So, I haven't really seen the need for a hierarchical IGP for the simple fact that I've always managed to find a way to make it work without having to put one in, and it may be something more with laziness than anything else, but we actually turned off the bits that were sort of leading us down towards the hierarchical IGP about a year or 2 ago. The convergence for most of the devices is well under sub-second. It's only these few devices that you know we can actually hide information from anyways, that we have left that are sort of slow. So, you know, I just sort of never really pushed it. So.
And the other comment is just on the use of IGP versus BGP for carrying end prefix information. Yeah,
definitely. You know, you don't need a whole lot in your IGP except for the loopbacks. Even the point-to-point interfaces, they don't, the IP parts of the point for ISIS at least don't necessarily need to be there. We do carry a little more. We might carry some phantom next hops, for example, to create an ECMP situation for traffic. So if I want traffic to hit two different nodes at the exact same time, I might, you know, BS the IGP into thinking that it's got a next hop on two different nodes and it's equivalent, and then it'd get forwarded there. But in general, we don't throw a lot in the IGP. Any other questions?